Hi everyone, so we're going to continue here talking about Earth's oceans. So when we're thinking about oceans here, all of our oceans are connected because our land doesn't ever have a full break in our water. So all of our oceans are joined into a singular interconnected body, and this is called our world ocean. So our world ocean plays a really important role with regulating our planet's environment. So we can see here some different divisions of the ocean, ones that we're familiar with. We're over here, and we can see that our side is our Atlantic Ocean, though our Pacific Ocean is actually our largest ocean that we're going to talk about. So looking at our Earth's ocean, our largest ocean is our Pacific Ocean, with a surface area of about 155,557,000 kilometers squared. So again, very, very large ocean here. And it's also going to have our deepest point in the ocean, which is called our Challenger Deep, or what you might actually know it as is our Mariana Trench. So if you look at our image on the side, we can see some of our different elevations in the world. So our highest mountain point here is at 29,000 feet. Our Mariana Trench actually goes down 36,000 feet. So it's actually our furthest point from surface, from sea level, compared to our tallest mountains to our deepest trenches here. So it's this Mariana Trench is located in the east of our Philippine Islands, and that is our bottom of the Mariana Trench. So if we're looking here, we can see how deep it is. So our sperm whale is the whale that can dive the deepest down into the ocean at only 3,000 feet. So if we continue to look down here, we can see that we have some boats here. Their final resting spots are still not as deep as our Mariana Trench here. So Earth's oceans, so our surface currents, move clockwise north of the equator. So when we're thinking about, remember dividing our Earth up into northern hemispheres and southern hemispheres, on the northern hemisphere we're going to see it moving clockwise. And on our southern hemisphere, we actually move counterclockwise with our surface currents in our oceans here. So, I don't know if you ever heard the myth that the toilet actually swirls the opposite direction in Australia. That is true because of that separation here with our surface currents. So in the north, our toilet's going to spin clockwise. In the south, we're going to spin counterclockwise. So if we take a look at some of these surface patterns, you can see if we divide here into north and south, we can see that up here we are moving in that clockwise direction, but we are moving counterclockwise in our southern hemisphere. So it's really going to be important to know those two differences here. So again, moves clockwise in northern hemisphere, counterclockwise in our southern hemisphere. So storms are not currents. So some of the storms that you've heard of, hurricanes, typhoons, cyclones, are all rotating storms that usually are created in our tropical areas. So because of this, our storms are going to rotate opposite of our currents in those areas. So in the northern hemisphere, our storms are going to rotate counterclockwise, and in our southern hemisphere, our storms are going to rotate clockwise. So it goes against the current, our storms here. So hurricanes are going to see a lot in the Atlantic, Northern Pacific, so U.S. Eastern Seaboard and U.S. and Mexican Western coasts here. Our tropical cyclones are going to be in the Western Pacific, so that's going to be more of China, Japan, Philippines, etc. Those are our typhoons. That's the word for those. And then in our southeastern Indian Ocean, southwestern Pacific, we're going to call these tropical cyclones actually cyclones here. So it's going to be more like in our Australia, southern hemisphere area. So talking more about our oceans, the second largest ocean is our Atlantic Ocean. So this is our second largest, covers about half the area that our Pacific Ocean does at 76,630,000 kilometers squared. Our third largest ocean is our Indian Ocean, which is going to cover about 73,762,000. And then our smallest ocean here is our Arctic Ocean, which only covers about 14,560,000 kilometers squared here. Our Arctic Ocean actually has pretty unique factors though, because it's covered in floating ice. So some of these you might think of glaciers or different things like that. So this forms when these wind and waves drive together frozen seawater and push it into a large, massive object. So it's kind of like flat area, so it kind of looks like it's covered in land, but it's actually just large ice, floating ice there. So there is a huge difference between our ocean water and our fresh water here. So talking about that difference here, our ocean water is going to contain more salts. That's going to be very important here. So salinity is what we're measuring when we're measuring salt. So it's the amount of dissolved salts in any given liquid. So salinity is in lower places where we get a lot of rain or fresh water flows into the sea. So those areas of runoff that we talked about in our water cycle. But in contrast, salinity is a lot higher in places where water evaporates rapidly. So when water evaporates, it leaves all of those salts behind. So that's going to increase our salinity in those areas. So our ocean currents are also driven by this amount of salinity. So most of the salt in the ocean is sodium chloride. So I'm sure this is a salt that we've heard of before. This is just classic table salt here. So it's made up of our elements sodium and chloride, which is pretty obvious here. And there are other elements that we can find in the ocean. So we can see here, we have our chloride, sodium. We also have magnesium here, sulfur, calcium, potassium, and some other elements in here as well. Something that we also see in our ocean are different temperature zones. So the deeper we go down, the lower the temperature is in our water. So our surface of the ocean is warmed by the sun, where the depths of our ocean, where sunlight never reaches, are very cold but just above freezing. So surface waters get stirred up by waves and currents, and below surface zone is our thermocycline. So I just want to look at this image right here. We can see our temperature gauge at the bottom. Temperature increases to the right here. So when we're looking, our deep water has a pretty consistently cold temperature here. Our thermocycline is getting mixed a little bit with our surface water, so our temperature is going to vary. And then our mixed layer, so our surface area, is going to be pretty consistent, and that's the part that's being heated by the sun here. So taking a look at some temperature zones. So our surface zone is the warmest layer of our water here, heats up here. Our thermocycline layer, like we said, mixes a little bit with the surface zone, but also has a range of temperatures, and you can really see that range here, how temperatures vary a lot in this thermocycline zone. And on our deep zone, it's going to be our lowest temperatures here, right below freezing at about 2 degrees Celsius. So our temperatures stay pretty consistent in our deep zone and in our mixed zone. So it's important to note that huge temperature variation in our thermocycline zone. So we are going to stop here for this one. Remember, if you have any questions, feel free to ask.